Hi everybody, welcome back. So just have a basic series circuit laid out for us, and we're going to use the convention of complex numbers to help us to go through and analyze this and just see how it is much quicker, it's much simpler. We have to have the fundamentals first to understand the displacement of these, but then we can go into this and solve it quickly, efficiently, and in a way that isn't going to involve a lot of steps. Because if there's a lot of steps, we're going to inherently make a few mistakes along the way. It's going to happen. So how do we remove that margin? How do we decrease that margin for error? How do we become more accurate so we're not making those mistakes time and time again? Well, simplify the process. Okay. So we're going to go through solve. We're going to do the impedance. I'm going to give you the voltage. And I encourage you to stop this and see if we come up with the same values in the end. If you have your process already ironed out, great. What I want to show you is a way to simplify it that's going to allow us to be quicker and to make fewer mistakes. So the first thing we're going to do is calculate the impedance. Then I'm going to give you the voltage, and then we're going to solve for the current. So I'll switch colors. So the impedance of this circuit, we know in a series circuit, as we add opposition in series, our total opposition will increase until I add, if I have a capacitor with the inductor, then we see some interesting things happen. That's why I just left it as an RL circuit. We'll stay there for now. But with understanding this convention, we can quickly solve for this. If we understand that as we add them, my total value must increase. So I know that three of these value, my resistive properties, they're all the same. They're a horizontal component. They're a real value. I can measure that with an ohmmeter. This XL, I cannot measure that with the device. Okay, it exists. It's a part of that coil. Okay, so if I put this is one device right here. This is a relay coil or something like that. In reality, like series circuits, understanding them is absolutely valuable, because any circuit, I don't care which one it is, any single circuit can be broken down and analyzed as if it were a series circuit. You can do the same with a parallel circuit, but a purely series circuit, this is a model for us to understand and break down the most difficult electrical circuits. We can break them down and we can simplify them into a series circuit, which is much, much easier to analyze. So when I'm doing this, I'm taking my resistance, my R1, plus my R2, plus my R3, plus my XL value. Now this is where it's really important that you don't just go 3 plus 3 plus 2 plus 6, because we know that this XL value, it looks familiar right here, R plus R plus R. I can add those, and then you look at this, well, it's different. You're right, it's different, so don't just add it directly together. This is where I'm going to use the convention of a complex number when I punch this into my calculator, and that's how I'm going to add this. So I'm going to have 3 ohms plus 3 ohms plus 2 ohms plus, and this is where I'm going to use the concept of an imaginary number, and 6 ohms. So when I go to compute that, I'm going to get an answer that's reflective that that is a vertical component. If I were to draw this out on a Cartesian plane, okay, we have moved 8 units to the right, 3 plus 3 plus 2. Okay, so there's my 8 units to the right. My impedance is moved to a value of an imaginary value of 6. So I know where that is going to fall. So you know you don't just add them directly together. But when I do add them with the convention of a complex number, I get 10 ohms. Okay? So it's 10 ohms is my impedance of this circuit. Another way that I could do this is so this is rectangular form. I'm using the horizontal and the vertical components. Okay. that 10 ohms is the value of the impedance. Okay, another way that I could do this is polar form, where I could have just said my 3 ohms is at 0 degrees, because we know that's a purely in-phase component. I have another 3 ohms at 0 degrees. I have another 2 ohms at 0 degrees, plus I have 6 ohms, 90 degrees displaced from there. So if you do that into your calculator in polar form, you would get the same. You would get 10 ohms. The nice thing about doing it in polar form is that now you have an angle. So I would have an angle of negative 36.869 degrees. Sorry, not negative. I have a positive value of 36, and that's my impedance value. That is the impedance of that circuit. So with rectangular form, all I'm getting is a magnitude. Okay? Rectangular form just gives me the fact that it's 10 ohms. So now if I give, with polar form, before I jump into the next, with polar form, I'm giving the magnitude and the direction of that value. Okay? So if I were to say that this is 120 volts at 60 hertz, and I wanted to know what my current is, this is nice and simple now. I'm going to do it in 2 different ways. I can do it with rectangular, or I can do it with polar form. Personally, I really like to do this in polar form because it's 1 step. 1 step means fewer mistakes. Okay? So, if I'm going to calculate the current, I'm going to take my applied EMF, divide it by my circuit impedance. And it's really important. We know in an AC circuit, angles are very, very important. So when I am calculating this, don't forget that angles are important. I have 120 volts at 0 degrees divided by 10 ohms at 36.869 degrees. And when I solve for that, and I place that into my calculator in that fashion, I will get 12 at negative 36.869. So 12 amps is my value at negative 36.869 degrees, which makes total sense. Because if my voltage is here, because I said voltage at 0 degrees, so voltage is on the x-axis. We know the principle with an inductive circuit is that current is going to lag voltage, so I'm going to lag, current is going to lag its voltage by an angle of 36.869 degrees. So I have 12 amps at negative 36, or you could subtract it from 360 to say definitively where you are at that point. So that's the necessity of understanding how complex numbers can greatly reduce our workload, is by understanding how we can quickly come to an answer, okay, without having to draw these elaborate other diagrams. We simplify this, use the convention of a complex number, okay, or we can use this by the angles that they're at with polar form. But this was a 2-step problem. Solve for the impedance, solve for the current. This wasn't the 4-step problems with more diagrams, more symbols, more calculations, and this took all of them into effect. So I hope this has helped, and I hope this is going to help us simplify things in the week to come. I look forward to meeting with you, and I look forward to seeing you in the next video.